Ideal spring and simple harmonic motion. Springs are familiar objects that have many applications, ranging from pushing button switches on electronic components to automobile suspension system to mattresses and others. In use, they can be stretched or compressed. For example, here, the top drawing, the figure shows a spring being stretched. Here, the hand applies a pulling force of Fx to the spring, which is parallel to the length of the spring. In response, the spring is stretched and undergoes a displacement of x from its original or unstrained length. So here at the middle is the unstrained length, or it's neither stretched or compressed. At the bottom drawing, you can see that the spring is being compressed by Fx. Now the hand applies a pushing force, and again it undergoes a displacement from its unrestrained length, which is x. So the experiment reveals that the relative small displacements that the force Fx required to stretch or compress a spring is directly proportional to the displacement x, which arrive us with Hooke's law, which states that the force needed to extend or compress a spring is directly proportional with its displacement. Or in symbol, we have Fx is equal to negative kx. Negative implies that the displacement and the force is always at opposite direction. Where in Fx, we know, is the restoring force. Let's say at the top drawing, the displacement is x, which is positive in direction, but the restoring force that the spring produces is negative direction, directed to the left. Or otherwise, when the displacement is in negative direction, the restoring force of the spring is directed to the right. And we have this k, which is the spring constant with a dimension of force per unit. So a spring that behaves according to this law is said to be an ideal spring. Sometimes the spring constant K is referred to as the stiffness of the spring because a large value of K means the spring is stiff, in the sense that a large force is required to stretch or compress it. Now we have simple harmonic motion. So a restoring force exerted by an idealized spring is directly proportional to the displacement, which obeys the Hooke's law, wherein Fx is equal to negative Kx. And the graph shows the relationship of Fx versus the displacement x in a straight line. So when the restoring force is directly proportional to the displacement from equilibrium, the oscillation is called simple harmonic motion. And it obeys the Newton's second law of motion, wherein the acceleration is equal to force divided by the mass. And if we substitute the value, or we substitute the mass, the force by kx, we have the acceleration is equal to negative kx over m. So, a body that goes harmonic motion is called harmonic oscillator. So, the minus sign here means that the acceleration and displacement is always have opposite sign or opposite in direction. Same with the force and the displacement. So acceleration is not constant. So don't ever think to use the constant acceleration equation that we have discussed in kinematics. Now, we already observed this with our simulation that when an object moves in a simple harmonic motion, a graph of its position as a function of time has a sinusoidal shape with an amplitude of A. So when a pen is attached to an object, it records the graph, as we can see here at the left figure. So sinusoidal shape is the same with the sine wave or the sine function in trigonometry. So this behavior or the way the body oscillate in horizontal motion is the same with the vertical motion. So when a spring is connected or positioned vertically and a mass is placed, it creates a simple harmonic motion with a sinusoidal shape of position as a function of time. So later on, we will discuss more about this sinusoidal shape of the amplitude or the sinusoidal wave of the SHM. By the way, SHM is the abbreviation for the simple harmonic motion. So why is simple harmonic motion important? Keep in mind that not all periodic motion are simple harmonic. In periodic motion in general, the restoring force depends on displacement in a more complicated way. But in many systems, the restoring force is approximately proportional to displacement if the displacement is sufficiently small. That is, if the amplitude is small enough, the oscillations of such system are approximately simple harmonic and therefore approximately described by our formula that fx is equal to negative kx. Thus, we can use simple harmonic motion as an approximate model for many different periodic motion, such as the vibration of the quartz crystal in a watch, the motion of a tuning fork, the electric current in an alternating current circuit, and the oscillation of atoms in molecules and solids. Now, let's have an example problem. We have here when a tire pressure gauge is pressed against a tire bulb, the air in the tire pushes against a plunger attached to a spring. Suppose the spring constant is K equals to 320 Newton per meter and the bar indicator of the gauge extends 2 centimeters. When the gauge is pressed against the tire bulb, what force does the air in the tire apply to the the air in the tire applied to the spring? So we have our given K, which is 320 Newton per second, and displacement of 2 centimeter. And we're looking for force or Fx. So Fx is equal to negative Kx, where K is 320 Newton per meter and K is and x is 0.02 meters. So don't forget to convert centimeter into meter so we may cancel out the unit of distance. Therefore, our force is equal to 6.4 Newton. Negative, indicating that it is a negative opposite in direction with sorry, there's some mistake. Okay, so it indicated in the problem, what force does the air in the tire apply to the spring? So meaning the force applied to the spring. Therefore, our displacement is the same direction with the force. Therefore, it should be positive. Okay? Again, take note that Fx is equal to negative Kx, wherein Fx is the restoring force of the spring. Okay? And in our problem, we have the question is what force does the air in the tire apply to the spring? Therefore, we are looking for Fx applied. Therefore, our Fx applied is equal to 6.4 Newton. And it is positive in direction. So I hope it is clear with you the difference between the Fx applied and the restoring force Fx. Now, let's have test your understanding. Try to solve this problem and write your answer in the comment section.